In this lecture, we will talk about probability. So first, what are probability experiments? By the definitions, a probability experiment is an action or a trial through which a specific result, which are outcomes, right? Counts, measurements, or responses are obtained. So you do an action during an experiment or a trial, and you get results from those actions or from those trials. Those are probability experiments. So let's look at some simple examples of probability experiments. First, if you draw a card from a standard deck of cards, it is a probability experiment. So you draw this card, you get a 7 of diamond, right? So 7 of diamond here is one outcome of this probability experiment, which is drawing one card from the standard deck of cards. If you draw another one, you get an ace of clubs. So we have an ace of clubs here. Again, this is one outcome of this probability experiment. Okay. Rolling a die, if you roll a die, you will get one outcomes, right? You get a 6. If you roll another die, you get a 5, right? If you flip a coin, you flip one coin, you get maybe a tail, and you flip 2 coins, maybe you get another head. So in summaries, you get 1 of 2 heads here. And if you look at this rolling die experiment that we just did, the sum of the 2 rows is 11. So 11 can be the outcomes of rolling 2 dice experiment, right? 1 of 2 heads can be the outcomes of flipping 2 coins. And then you get 2 cards drawing from a 52 cards. It is an outcome of drawing 2 cards from a standard deck of cards. So these are simple probability experiments, and you can see that you can figure out the outcomes of each experiment. And once you know, once you identify a probability experiment, you can talk about a sample space. By the definitions, the sample space is a set of all possible outcomes of a probability experiment. For an example, if you drawing a card, right, from a standard deck of cards, your sample space should be 52 different distinguished cards. If you roll a standard dice, a 6-sided standard dice, then the sample space of rolling a die should be 6, right? 1, 2, 3, 4, 5, 6, because those are all the possible outcomes that you can get from rolling a die. And when you flip a coin, the sample space for flipping one coin is just either a tail or you get a head, right? So 2 possible outcomes for flipping a coin one time. Okay, and then what is an event? An event is a subset, right? It's not all the possible outcome. It's just a subset of the sample space, which might could be 1 or more outcomes, right? So an event in drawing card could be drawing a heart, or drawing a diamond, or drawing a club, or drawing a spade. An event in rolling a die can be rolling die that is greater than 3. So all the possible outcomes in that event is 4, 5, 6, because whenever you roll a die that is greater than 3, that is how that event defines. For flipping a coin, an event can be just getting a tail or getting a head. All right, so let's look at the first example. If the question is tossing a coin a probability experiment? And the answer is yes, right? Because when you toss a coin, you get either a tail or a head, and you get like tossing a coin is an action, and then you get an outcome out of it. So if it's yes, then what is an outcome of this probability experiment? So tossing a coin, there's only two possible events. It can be getting a head or, right, another outcome is getting a tail. Okay. And the next question is, what is the sample space of this probability experiment? So the sample space is a set, right? Set that contains all the possible outcomes. So this event, you only tossed a coin. So all the possible outcome is you're getting either a head or you are getting either a tail. Okay. What is an event of this experiment? And this is a very simple experiment. So an event of this experiment is flipping a coin and getting a tail. Flipping a coin and getting a head, right? So very two simple events that you can get from this experiment. Okay, go to the next example. Now, the experiment is tossing a coin and rolling a die. Also, this is also a probability experiment because you have some actions and you get results, right, and outcomes out of those actions. Cool. So yes, it is a probability experiment. So the question is, what is an outcome of this probability experiment? Again, you tossing a coin and you rolling a die. So let's go back here. Tossing a coin, right? And you roll a die. So getting a head and a 4 is an outcome of this probability experiment. Say, getting a head and a 4, right? Is there another outcomes? Yes, for sure. So tossing a coin and you're rolling a die. So now you get a tail and a 3. It's another possible outcome. A tail and a 3. So these are just two possible outcomes of this experiment, right? It's not all of them. Now we can talk about what is the sample space of this probability experiment. So again, the sample space contains all the possible outcomes. So you can see that when you flip a coin, you can get either head or tail, right? And when you roll a die, you can get either 1, 2, 3, 4, 5, 6. So for a head, you can get 1, 2, 3, 4, 5, 6. Okay, so you get head 1, 2, 3, 4, 5, 6. Also, if you flip a coin and you get a tail, then you also have other outcomes is tail 1, tail 2, tail 3, tail 4, tail 5, and you get a tail and a 6. So these are all the possible outcomes for this experiment, tossing a coin and rolling a die, okay? And the total number of possible outcomes that you can count is 12, okay? So the next question is, what is an event of this experiment? So an event of this experiment can be, what is getting ahead and getting an even number. Okay. So this is one event, right? This is an event. And this event is described by getting ahead and getting an even number. So, and all the possible outcomes in this event, right? Possible outcomes of this event is, you get ahead, right? And you get an even number, so 2 ahead, and a 4 ahead, and a 6. So these 3 outcomes are all the possible outcomes of this event, right? It's not the possible outcomes of this experiment, but it's these are the possible outcomes of this event. Now we can talk about the fundamental calculating principle. The reason why we want to talk about this principle is this principle will help you find the size of the sample space, which is all the possible outcomes of an experiment. Because this information here will be very helpful when later on you will try to find what is the probability of getting ahead and getting an even number using the total possible outcomes of the event and then total possible outcomes of the experiment. So the principle says, if one event can occur in m ways and the second event can occur in n ways, then number of ways the 2 events can occur in sequence is m times n. So this rule can be extended to any number of events occurring in sequence. All right. So to explain this principle, so if you look at this probability experiments, there's 2 different events going on, right? First, you toss a coin, and second, you roll a die. Okay. So when you toss a coin, there's only 2 possible outcomes for tossing a coin, which is 2 possible outcomes, which is getting a head or tail, right? For rolling a die, you get 6 possible outcomes, 1, 2, 3, 4, 5, 6. So if you doing an experiment when you toss a coin and roll a die in sequence, right? To toss a coin and you roll a die at the same times or in sequence, then the total number of all the possible outcomes for this experiment is 2 times 6, which is you get 12 here, right? So 2 is head and tail, 2 is head and tail, and 6 is just the possible outcomes of the die. So 12. Now, if we look at this example here, well, we should talk about the example number 2. So for a coin, the 2 possible outcomes, which are head and tail, right? For a die, there are 6 possible outcomes, which are 1, 2, 3, 4, 5, 6. So the total possible outcomes (2 times 6 equals 12), and we can verify it up here. All right. Now let's look at example number 4. So say if you go to a pizza store, right, and you have a bunch of different selections for crust, for sauces, for meats, for vegetables, then you want to count how many possible different pizzas can you choose from this menu? When you have 3 choices for crusts, you have 3 choices for sauces, you have 4 choices for meats, and you have 1, 2, 3, 4, 5 choices for vegetable. Then the total possible possible different pizzas that you can choose from this menu is 3 times 3 times 4 times 5, which is 120. 20 times 6 is 120. Okay, so you have 120 different kinds for picking up pizzas. Now we can talk about types of probability. So there's 3 different types of probabilities. The first type is the classical or theoretical probability. And this probability this probability is used when each outcome in a sample space is equally likely to occur. The classical, in order to find the probability for classical probability, the probabilities can be given by this formula here. So in order to find the probability of the event E in a classical probability, you find the number of outcomes in the event and you divide it by the total number of outcomes in the sample space. Again, in order to find the probability of a certain event in classical probability, you just calculate, right, the number of outcomes in the event divided by the total possible outcome. So let's look at the example number 5. Roll a 6-sided die. This is a classical probability because if you roll on a die, the chance of each of the side showed up are equal. The chance of each sides, right, that showed up after one roll is equal. So then you can answer the questions. What is the probability of rolling a 3? So rolling a 3, so events, this is an event, right? And rolling a 3 only has one outcome, which is a 3. And the probability of rolling a 3 is equals to 1, which is the number of outcomes in this event, and divided by 6, which is the total possible outcomes. This is the number of outcomes in this event, and 6 is the total possible outcome. Which is getting a 3. All right, so the answer is 1/6. How about what is the probability of rolling a 7? Can you roll a 7 using a 6-sided die? No, then the probability should be 0/6, which is 0, right? What is the probability of rolling a number less than 4? So how, this is an event, right? Less than 4 is an event. And in order to find this probability, less than 4, you take the number of outcomes in this event. How many outcomes in this event that you can count? So less than 4, you get 1, 2, 3. So you have 3 possible outcomes. And then divided by the total outcomes, which is 6. And you can simplify as 1/2, right? There's 1/2 chance that you can get a number that is less than 4. Then the next types of probabilities is empirical or statistics probability. So this probability is used when you observe, right? The observations are obtained from probability experiments. So you can distinguish between classical and empirical probabilities based on the classical probabilities is based on the theory. You know that in theory, this is the likelihood of getting this outcome. And in empirical, you have to collect, right? You have to have some observation. You have to collect the responses from the experiments. For example, if you do a survey, and then you collect responses from your sample, and then you will get some responses, right? Some numerical responses according to each classes or according to each categories that you are surveying. So then you can use those number from the survey, the result from the survey, to compute the probability. And this, when you do that, this is when you do you're using an empirical probability, or you're using an empirical probability experiment. So in order to find the probabilities of an event E of the empirical probability, and actually the empirical probability of the event E is just the relative frequency of the event E. Relative frequencies is the frequency, right, over the total frequency. The frequencies of each category over the total frequencies. And when you're talking about event, the event can be a category. So the probabilities is equals to the frequency of E divided by total frequency. And if you remember the distributions, frequency distributions, it's just F divided by N, when N is the sample size, okay? And F is the frequencies for each class or frequency for each categories. Let's look at the next example. So in this next example here, the table shows the results of a survey, right, in which 142 male and 145 female workers, ages from 25 to 64, was asked if they had at least 1 month's income set aside for emergency. And this table here shows the results of that survey. So you can say that this is female column, this is male column, this is female column, and this is the total column. And you have the first row is showing how many people have less than 1 month's income, and the second row showing how many people, how many responses that have 1 month or more than 1 month of income. And it's the total of all the rows, all the columns here. All right. So if you look at this table, and when you ask, what is the probability that randomly select a worker is female? So the event is selecting a random worker that is female, right? And you can see that how many female do we collected? 145. So the probability of this event I call this is event A, okay, equals to the total outcomes of the events, which is female, divided by the total outcomes of the sample space. And the total of the sample space is, the outcomes of the sample space is 287. Okay. And you can keep it this form, or you can compute it using decimals, it's up to you. But you can just keep it as a fraction. Again, if you select a random worker and you ask what is the probability of getting a female from a randomly selected worker, it should be the total number of female in this survey divided by the total number of responses. B, what is the probability of selecting a random worker that has less than 1 month's income for emergency? So you select, so I call this is event B. So the probability of B should be equals to, so what is, how many outcomes in this event B? Less than 1 month's income. So I go to the less than 1 month's income, total is 149, okay? And again, if you're randomly selecting a worker, right, then you have to divide it by the total responses. So 249 divided by 287 is the probability of randomly selecting a worker that has less than 1 month's income. All right. C. So find the probability that randomly select a worker has 1 month's income or more. Okay. Given that the worker is female. Okay. So I call this event is C. So the probability of C is, so first the event is the worker has 1 month's income or more, which is 1 month income or more right here, given, right? But then now you're not looking at the whole entire populations. You're not looking at all the responses. You're just looking at the responses that are from female. So that means I would take 1 month incomes, 62, and then I divide it by the total number of responses from female, which is 145. Again, if you want to find the probability of selecting a random worker that has more than 1 month's income, and given that the worker is female, that means you reduce the populations down to only looking at female. And the total number of female responses from female is 145, and 62 is number of them who responded to have more than 1 month or more than 1 month of income for emergency. Okay. So the last one, find the probability that randomly selected worker is female. And I call this, so this is D. So what is the probability of selecting a female given the worker has less than 1 month income? 1 month's income, right? So the probability of D here is, again, the total possible outcomes for female is, and given that worker has less than 1 month. So this is the population that we're looking at right now. The worker that has less than 1 month's income. And then how many female? 83. Okay, what is a possible, what is the total number of responses that has less than 1 month's income is 149. This is the probability of picking a female. If you look at, so again, you reduce the populations down to just the responses that have less than 1 month's income, right? And the total is 149. And what is the probability of picking a female out of this population, subpopulation, is 83. So the answer for this question is 83 over 149. Again, if you have a survey, you're collecting the responses, and you put in a table that have the other categories. So less than 1 month's income is one category. 1 month's income or more is another category. And you have female is another category, and you have male is another category. In order to find the probabilities of any given event, you need to look at the total possible outcomes of each event. And then you have to look at the total outcomes of the sample space. For A and B, the sample space, because you just randomly pick a worker from this survey, that means the sample space has to be the total number of responses. For C and D, your question changed a little bit. So you can identify the event, right? But then you have to pay attention to the sample space. So the sample space in C is just female. And the total number of females, responses from female is 145, right? For D, the sample space for D is just a worker that has less than 1 month's income. And then you have to look at this row here. And the total number of workers that has less than less than 1 month's income is 149. So the sample space has to be 149. So pay attention to the event and also pay attention to the sample space that you're looking at. Now that we talked about classical probability and empirical probability, right? Then maybe we want to discover, trying to explore how they related to each other and in which way. And I will look at looking at an experiment here. So this is an experiment when I flip 16 coins with an equal chance of getting a head and a tail, right? So I flip 16 coins with probability of head is 0.5. That means it's a fair coin. You have a half chance of getting a head and you have a half chance of getting a tail. And you flip 16 coins, then I want to count how many heads will I have after flipping a coin 16 times. So it's saying the 10 heads here. So you flip a coin 16 times, you get 10 heads, okay, for one time. If I flip a coin another 16 times, I get 9 heads in this experiment. Okay. Again, I run flip another coin 16 times, I get 7 heads, and so on and so forth. So you might wondering if I repeat, this is a probability experiment, right? If I repeat, and in theory, if you flip a coin 16 times and the probability of getting a head is 0.5, like a half chance, that means in theory, you should have 8 heads after 16 times of flipping a coin. But as you can see that I've run this experiment 3 times, I didn't get 8 heads. I got 9 heads, I got 10 heads, I got 7 heads. And this time, I even get only 6 heads. So that means, and the experiments I'm doing here is empirical experiments, right? I'm flipping it 16 times and observing the outcomes of my experiments. Few times. I run another time. I got 11 heads. I even got 11 heads. None of the times that I have experiments, this will get me 8 heads. But what if I run this experiments, right? I flip a coin 16 times, 1,000 times. Then you can see that the number of heads here and this, so you see this is the histogram, more or less like a histogram, right? The x-axis is the number of heads and the y-axis is the frequencies, how many times that you get this number of heads. And if you run this experiment 1,000 times, you can see that I have a symmetric distributions, right? And you can see that this is more or less like my, and this area here, the middle area here, is the mean or the median and also the mode of my distributions. So you can see that this bar here is the number of heads, right? Is 8. 8 is the number of heads, is 8 here, is happens the most frequent. So flipping a coin 16 times, 1,000 times, right? You repeat this experiment 1,000 times. Most of the time, and the most frequency, the mode of this experiment or this distributions is actually 8, which is the same as if we use empirical, we use a classical probability. We guess that we get A hats out of 16 times in theory. Well, in practice, if we flip it 1,000 times, you do get A hats most of the time, right? The mode of this distributions here is actually 8, and you can see that the distributions is symmetric, and the means number of hats that you get is around 50%. And when you look at this graph right here, this is tell you the proportions of, right? So the X is the number of runs, Y is the number of proportions that is greater than A hats, right? The number of hats here, and you see the proportions, if I change this to equals than, greater than or equals to A, then this this convergence here is converging around 0.5 or 0.6. Proportion 0.6. Okay, so that's saying if you repeat an experiment, right? If you repeat an empirical experiment a lot of time, then the result of empirical probabilities approaches to the result of the theoretical probability of an event. So that is the law of large numbers. Again, the law of large numbers saying that an experiment is repeated over and over again, right? The results that you get from the empirical probability will converge or will approach to the result that you will get from a theoretical probability. It is a law of large numbers. Okay, so the last type of probability is subjective probability. So subjective probabilities result from intuitions, right? Or educated guesses, or from estimates or experience, prior experience. And some examples of subjective probabilities are: a doctor may feel that a patient has 60% chance of full recovery. So the doctor can make these estimations based on his prior experience. Or a business analyst may predict that the chance of employees of certain companies going on strike is about 25%. So he predicts this chance based on his experience. Now let's look at some exercises here. So in this 4 probabilities, you want to distinguish, you want to classify types of each of the probability of each of experiments, right? According to a company records, the probability that a washing machine will need repairs during a 6-year period is 0.1 or 10%. So if you have a record from a company, in order to come up with this estimations, that is when you use empirical probability or statistics, right? Because you use the records in order to come up with this number. According to a survey, the probability that an adult chosen at random is in favor of sprinkling ban is 0.45. So if you use a survey, then again, it is an example of empirical probability. A probability that randomly select a number from 1 to 100 is divisible by 6 is 0.16. So this is a number that you get from theory, because you can actually count the number of the divisible by 6 number from 1 to 100, and then you can find the probability of that. So this is why it's a classical theoretical probability. Okay. You did not use any surveys. You don't have to do any observations. You actually can count the exact number that are divisible by 6 from 1 to 100. Okay, you think that the probability of a football team's probability of winning its next game is about 80%, right? You think that means you don't have any survey, you didn't have any surveys, you don't have any theory, you come up with this numbers, right? With this probabilities based on your experiments. So this should be subjective probability. In this section, we'll talk about the complementary events of probability experiments. First, let's talk about a standard deck of cards. So in a standard deck of cards, there are 4 kinds of cards. There's hearts, diamonds, clubs, and spades. So in each kind, there's 13 cards ranging from 2, 3, 4 to 10, and then Jack, Queen, King, and Ace. Well, if you pick a random card from a standard deck of cards, it is a theoretical probability experiment. And the sample size or the sample space of this experiment is 52 because there are 52 cards. Examples of events of this experiment could be, picking a heart, picking a 7, or you picking a black card, etc. Now here's an example of an event, like finding the probability of an event in this experiment. So if you pick a random card, what is the probability of getting a queen of any kinds? So keep that in mind that in order to find the probability, a theoretical probability, you want to find the total number of outcomes of the event, and then you want to find the sample space. So in this event, there's 4 queens in a deck of cards. So the total number of outcomes is 4. And the sample space is 52. So the probability of getting a queen is 4 over 52. What about if you pick a random card, and what is the probability of not getting a queen of any kinds, right? So you can pick any card, but not a queen. So then again, we want to count, the number of possible outcomes of this event. Could be, a 4, could be a 6, could be a 9 of diamonds, and so on and so forth. So we counted, and we found that there's 48 of them. And the probability will be 48 out of 52. And we noticed that if you take the sum of 4 and 48, you get 52. So 48 equals to 52 minus 4, right, over 52. And then you can split it into 2 different parts, which equals to 1 minus 4 over 52. And you can notice that 4 over 52 is the probability of getting a queen of any kinds. So these 2 events are like directly related. One is, getting a queen, another one is not getting a queen. So let's look at the sample space of this experiment. The gray, space here is a sample space, the entire sample space. And if you pick 4 queens, and this blue space here is the probability of getting a queens, and we found that is 4 over 52. And then the green space here is the space for the outcomes of not picking a queen, which is the second event. in the previous example, and we found the probabilities is 48/52. We can see that the space, the green space and the blue space is a complement of each other. And when you add the two spaces together, you get the entire sample space. We notice that the sum of these two probabilities is equals to 1. That means, the outcomes of any of the trials falls into one of these two events. Pick a card is either a queen or it's not a queen, right? These two events are not overlapped, right? Either one or the other. And the probabilities of the two events is equals to 1. If two events satisfy these two conditions, then these two events are called the complementary events of each other. So picking a queen and not picking a queen are the complementary events of each other. Let's look at another example. Let A be the event of getting a number from 2 to 10, and B be the event of getting a heart of any card. The question is, are A and B the complements of each other? Why not? So if you look at event 8 and event B, and I pick an example, 5 of hearts. 5 of hearts belongs to event A because it's a number from 2 to 10. Also, it belongs to event B because it's a heart. You can see that these two events share at least one outcome, and that means they are not mutually exclusive. So event A and B are not mutually exclusive. Versus if the two events do not share any outcomes, then they are mutually exclusive. It's a reminder that, picking a queen and not picking a queen, these two events are separate. They do not share any of the common outcomes. So that means they are mutually exclusive. Also, in the event A and B, you can find the probability of the two events, and when you add the sum of the two probabilities, you don't get 1. So this is another condition in which we can use to make the conclusion that A and B are not the complements of each other. So from this example, we can formalize definitions for complementary events. So event A is called the complementary event of event B if and only if they are first mutually exclusive and the sum of the probabilities equals to 1. We usually use A to C to be the notations of the complements of event A. And as a result, P of A plus P of AC equals to 1. Let's look at another example. Let event A be an event that get a heart or a diamond. And the question is, what is the complements of A? Complements of A should be not getting a heart or a diamond, or getting a spade or a club, right? So if you get a spade, so it's a complement of getting a heart or a diamond. When you find the probability of A, so since there are 13 hearts and 13 diamonds in the deck of cards, then the probability will be equals to 13 plus 13 divided by 52 equals to 1/2. And the probability of AC, which is the probability of the complements of A, will be 1 minus the probability of A equals to also 1/2. And again, we use AC as a complement of A. Now, let's look at an example. In this example, there are 10 cards that are faced up. So in a standard deck of cards, there are 52 cards, and 10 of them are already dealt, or you already put them, all the cards faced up, and the rest 42 cards are still face down. And then we want to draw the next card in the deck, right? Then you are wondering, so what is the probability of getting a jack? We see that there's 2 jacks on the table, right? 2 jacks are faced up. That means in the pile, there's 2 jacks. So the probability of getting a jack is 2 over 42. Now, what is the probability of getting an 8? There's no 8 on the table. So there's still 4 8 in the pile, meaning the probability will be 4 over 42. What about probability of the complements of 7, which means, what is the probability of not getting a 7? So we can find the probability of getting a 7 and subtract it from 1. So probability of getting a 7 is 2 over 42, because there's 2 7s are on the table, there's 2 in the pile, and then you subtract 2 over 42 from 1 to get 40 over 42. So there's a very high chance of not getting a 7. The next question is, so what is the probability of getting a jack or a 7? So getting a jack or 7, these 2 events are mutually exclusive, right? So then, to find this probability, you want to find the probability of getting a jack, and you add to the probability of getting a 7. That will give you 4 over 42. The next question is, what is the probability of getting a diamond? There is 3 diamonds on the table, and there's total of 13 diamonds. So then there are 10 diamonds in the pile. So the probability of getting a diamond is 10 over 42. The last question, what is the probability of getting a club? Not getting a club. So there's 3 clubs on the table. That means there are 10 clubs in the pile. And then finding the probability of the complements should be 1 minus 10 over 42, which is equals to 32 over 42. So here's some examples of how to use probabilities, or how to calculate probability of some events and calculate the probability of the complement events of a certain event using their definitions, their properties. Main properties that is, if the 2 events are complements of each other, then the sum of those probabilities has to be 1. All right. So the first applications that I want to introduce is finding the probability of being a Mega Millions winner. How does it work? Here's how to play it. So a ticket costs $2 per play, right? Player may pick 6 numbers from 2 separate pools of numbers, 5 different numbers from 1 to 70, the white balls, and 1 number from 1 to 25, the gold mega ball. You win the jackpot by matching all 6 winning numbers in a drawing. So in order to calculate the probabilities of being a winner, you need to match all the 6 numbers, right, of drawing. So that means I can try to find what are the total possible numbers that can be drawn. So there's 6 numbers, 1, 2, 3, 4, 5, 6. So the first 5 numbers are from 1 to 70. So I would have 70 possible outcomes for the first number, 70 for the second number, third number, fourth number, fifth number. And for the gold ball, you have a choices. You have choices from 1 to 25, so you have 25 choices here. So the total number of other possible drawings are so using the fundamental counting principle, you can find the total possible drawings equals to, let's say, 70, right? Times 70 times 70 times 70 times 70 times 25, which will give us the number is 4.2 times 10 to the 10. Huge number. Huge number. So if you buy one ticket, that means you just pick a drawing, right? A possible drawings, which is 1. And then you have to divide it by all the total possible drawings, which is 4.2. And if you use a calculator, the number is very, very, very small, to 0. What does it tell you? That tells you if you only spend $2, right, buying a ticket, this is the chance of winning this lottery. The chance is, again, very, 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 very small. All right, the next applications is about access code. So an access code consists of 6 characters. For each character, any letter or number can be used, with the exceptions that the first character cannot be 0 and the last 2 characters must be odd numbers. So again, before finding the probabilities, you need to find the total possible outcomes or the total possible passwords. And this passcode consists of 6 characters. So 1, 2, 3, 4, 5, 6. So the first character cannot be 0. But for each character, any letter or number can be used, right? But the first character cannot be 0. That means the total possible outcomes for the first character is, so you have 10 numbers and 26 letters. So total you should have 36, but it cannot be 0, so you have to subtract it by 1, so 35. Letter, number, so number is 10, this is 26, okay? Okay, so, and the last 2 characters, this one here, must be odd numbers, must be odd numbers. So how many odd numbers we have? 1, 3, 5, 7, 9. So it's only 9 of 5. So there's 5 odd numbers. And these are the possible outcomes for the last 2 characters. For the rest of the characters here, you can put 36 in there. Okay. So the total possible outcome should be the products of all of these numbers. I found it, the total possible outcomes is 40A240000. These are the possible outcomes. So then using this information, you can find the probabilities, right? If you first time, right, you get the correct access code on the first try, that means you only try it once. So your the number of outcomes in the event is only one, right? Correct. Divided by total possible access codes that you can generate using this rules. Okay. Again, the probabilities of getting the correct access code on the first try is pretty small. And the next question is, what is the probability of not selecting the correct access code on the first try, right? Not selecting the correct one, which means is the complement of selecting the correct one. So the probability of incorrect. Right, equals to 1 minus the probability of the correct one, which is 1 minus 1 over 4082400. And again, this numbers again is very small, or very big, sorry. So getting the correct one is small, very small, around 0. Getting the wrong one, which is really big. So that means if you want to try to guess an access code randomly, this is the chance of getting the correct one, and this is the chance of getting the incorrect one. All right. So the last examples here is about the ability of medical testing. Okay. A new disease, right, randomitis, has been detected in an inhabitants of a city A, right, out of 1,000 people in that city. So this is a city A, and in this city, there's 1,000 people. 900 are disease-free, but unfortunately, 100 people have it. So I say this is 100 people who has the disease, right? And 900 who do not. Okay. A lab just developed a test in which 90% of the people who have the disease are diagnosed correctly. So that means within 100 people who got the disease, only 90 of them got the positive test, and 10 of them will get the negative test, because only 90% are diagnosed correctly. Okay. And 10% of those who don't have it, who don't have the disease, are incorrectly diagnosed. What does it mean? That means if 900 people here got tested, 810, right? 10% of them will get a positive test, and then the rest, which is 810, will get the negative test. Again, this is the healthy population, and this is the not unhealthy populations. So if a person from this whole city, right, from the 1,000 people, is selected to have a test performed on them and receive a positive diagnosis. So this is the conditions. This person's receive a positive diagnosis. What is the chance that this person actually have the disease? So the probabilities in this event, I call this is event A, right? So if you pick a random one person's in this city, and then and put a test on them, and the test came out positively. But what is the chance of this person actually have the disease? Because you see that you have some people from the healthy population got a positive test. Some people from the unhealthy population got negative tests. So there are inefficient tests. There are inaccuracy here when you use this test. So talking about this probably in this event, right? So you have to find the total possible outcomes, right? So the population that we narrow down to the population who receive a positive diagnosis. And the positive diagnoses are 90 people here and then 90 people here. So 90 plus 90. This is the total possible outcomes for people who get a positive test. Okay. But then what is the total possible outcomes of these events when the person actually has a disease? If the person actually has a disease, so the number of people has a disease in the unhealthy population got the possible positive test is only 90. Again, you can only detect 90 people in these populations. The 10 other people, the test failed to detect it. So that means the probabilities of a person who receive a positive test actually get a disease is only 1/2. What does it tell you about this test? This test is not a really reliable test because if you test positive, the chance of getting the disease is only 50%. But then if you did not calculate these probabilities correctly, you say, oh, 1,000 people, only 90% got the test diagnosed correctly, and then only 10% are misdiagnosed in this population. But turns out that in this case, this test is not a very good test because if the probability is only 1/2, either you get it or not, it's not a good test at all. It's just flipping a coin. When you say you test one person, put a test on one person, flip a coin and say, oh, you have a disease, or you're not, based on the outcome of the coin, not based on the outcome of the test. All right, again, this lecture is on the probability. And in this quarter, in this class, this is how much of the probability that we're gonna cover in this class.